our knowledge and skills advance, we work our way into the world of the ultra-small. It took 400 years from this to moving single atoms. Electrons have replaced light, but our quest into nanospace remains. Birth, growth, reproduction. In creatures this size, about a millimeter across, the whole spectrum of life falls to our watchful eye. Our insatiable curiosity leads ever deeper into the heart of things. The microscopic world permits us rare glimpses into the exquisite workings of nature. We watch nature and we copy her with varying degrees of success. As nature grows crystals, atom piled on orderly atom, so we are trying to emulate nature by building machines using protein molecules. Ambition is already leading us to consider making devices like this protein-bearing. In part, we base our attempts on nature's own mastery of machine building. For billions of years, protein-built rotary motors have powered the flagellae of microorganisms swimming in water.
Welcome from your guide to nanospace, a dimension which is all around us. It even comes man-made, built into our wristwatches, for example. On this program, we're going to venture into worlds of nanospace technology which we humans are creating. That means everything from wristwatch gears to, well, we'll see. This, of course, is a very special machine. The nanogate can shrink us into any space. This is a good place to start looking into man-made nanospace. We're inside a wristwatch. This is a world measured in tenths of a millimeter. And I, your humble servant, am but 2/10 of a millimeter tall. The gear beside me is the one that moves the second hand. Appropriately, it's the smallest in the watch. The slightest irregularity in a watch cog soon causes wear. So, although we're already dealing in tenths of a millimeter, these cogs have to be machined to a precision measured in thousandths of a millimeter. A first step in nanospace machine technology will be to make gears much smaller than this and do it as precisely as possible. We have a long way to go when even a commonplace object like a wristwatch demands such high-level machining technology.
Meet Bugsy, a light-seeking robot the size of a large garden pea. Bugsy travels around by means of a wristwatch motor and gears. It started life as an entry in a 1991 Japanese micro-robot contest. In fact, Bugsy is essentially a rebuilt wristwatch. It is the brainchild of a watchmaker, Mr. Miyazawa. Miyazawa used micro-machining technology developed by the watch industry for miniaturizing its products. Bugsy is, as the saying goes, more than the sum of its 97 rebuilt watch parts. It embodies light sensors reporting to an integrated circuit, the robot's brain. Miyazawa found that his major challenge was keeping Bugsy's mechanical parts as small as its electronic ones. Bugsy is not yet a household word, but given a few years, who knows? One day, it may prove to be a harbinger for a new generation of hazardous duty robots. For now, Bugsy goes to the strongest light source, moving fastest when the light is most intense. Miniature robots open possibilities to all sorts of applications. And why use just one when you can harness 8? Bugsies could inspect nuclear plants or pipes. They might be inserted to repair machines, where otherwise the machines would have to be taken apart. Medical robots in the bloodstream might inspect or treat disease directly. A future that is rushing towards us hides 1,000 possibilities. But to realize them, micro-robotics needs new technologies. For example, researchers at Case Western Reserve University use semiconductor technology to make micromotors. Given that semiconductor technology on this scale is less than 30 years old, its achievements are remarkable. In 30 years' time, making micromotors might be routine. This is the world's smallest man-made motor, compared with the thickness of a human hair. It is built on a silicon wafer, the material from which semiconductors are made. 1/10 of a millimeter across. It turns at 10,000 revolutions a minute. It is not enough to create the world's smallest man-made motor. Micro-robots must be able to grip things. Researchers at Tokyo University are trying to give them muscles so they can do just that. Measuring 0.5 millimeter by 1/10, these complex three-dimensional devices are also built on silicon. Looking like interlocking comb's teeth, the two components work together as synthetic muscles. The narrow point in these teeth is just 0.03 of a millimeter across. To activate these muscles, the researcher has to position 4 electrodes on a chip. When he applies a voltage, the combs attract each other and come together. Remove the voltage, and they move apart. The idea is to use this attractive force to power micro-robots. A range of new components will be needed if micro-robots are to work. Combined with tiny rotary motors, this electromechanical muscle gives the industry a promising boost. In the world of micro-robotics, this device has attracted a lot of attention. On the Berkeley campus of the University of California, the Berkeley Sensor and Actuator Center leads the world in using semiconductor technology to miniaturize machines. The center is working to develop several moving devices built on silicon wafers. Demonstrated by Dr. C.J. Kim, The world's smallest pair of pliers, produced on a silicon wafer, measures just 0.5 millimeter long. To make it work, the Berkeley micro gripper uses comb-type actuators, similar to Tokyo University's micromuscles. The slight flow of current across its actuators lets the gripper flex its muscles. This computer chip is enormous compared to the size of the instrument, the micro gripper which it serves. The pliers themselves poise like the stinger of a wasp on the right-hand end of the chip. Even at this experimental stage, the micro pliers are versatile enough to pick up a single microorganism. This image speaks volumes about the importance of, say, microsurgery in nanospace. Nanosurgery has enormous potential in gene splicing and other aspects of biotechnology. To date, microrobotics research is surging ahead without a clear vision of where it might lead. As new tools fall into place, who can doubt that potential new uses are not far behind?
A giant ant, dead, I hope. And next to it, an old gear wheel from a wristwatch. It looks as though we stumbled into a dusty, long disused crack in the floorboards of nanospace. Now look more closely, over there, not far from the ant's front leg. A cogwheel smaller than an ant's foot. At 35,000ths of a millimeter across, the whole thing is no bigger than a pollen grain. You might say I'm allergic to my work. There's another danger. Since these are the smallest gears in the world, I might just blow them away.
Madison, Wisconsin. Making the smallest machines requires one of the largest. These radiation doors conceal the University of Wisconsin's particle accelerator. This huge device at the radiation center cuts fine, smooth, tiny cogwheels. 120 meters across, the accelerator drives electrons to velocities approaching light speed in order to generate high-intensity X-ray fluxes. Like powerful lasers, the X-rays are used to machine the teeth of the cogs to high tolerances. Ultraviolet light is usually used to print the circuit patterns of semiconductor wafers. Shortwave ultraviolet is accurate enough for microcircuit boards. But if it were used to cut cogs, their outline patterns would be fuzzy. Only X-rays with an even shorter wavelength can etch these shapes precisely. The process works like this. First, a mask bearing the intended pattern of the gear is put into the radiation device. As a next step, a high-energy X-ray beam will print the original pattern onto a silicon wafer. X-rays leave an irradiated area on the wafer, which is later dissolved. The resulting template is used as a mold for creating the cogs. Since the gears are the size of pollen grains, recovering them demands ultra-clean facilities. The irradiated chip dissolves in a special solution, leaving only gears behind. At this point, the high-energy physics of a particle accelerator is replaced by more down-to-earth science, involving chemical etching and petri dishes. As a final step, gears the size of pollen grains have to be isolated and extracted from the solution. The best way to do this is to treat them as if they were coffee grinds with filter paper. At first, nothing is visible on wet filter paper. As it dries out, tiny dark specks dot the surface, like islands reappearing after a flood. A careless breath now could blow away several thousand gears. The result? A selection of the world's smallest gear wheels seen with the aid of an electron microscope. A silicon wafer the size of a small fingernail can be rendered into more than 10,000 cogwheels this size. Now begins the work of testing them. Researchers are making experimental gear trains and running them to test precision. The motor is at the center, a comparative giant, a quarter of a millimeter across. The true test is to see if the gears mesh smoothly. Hubs as well as gears were produced by radiation etching. Then the train was put together under a microscope. With gear trains like this, with visual sensors, muscles, and microgrippers, the dream of reducing miniature robots like Bugsy from pea-size to something in the order of a millimeter across is beginning to look possible from a technical point of view.
These gears represent one among many thrusts into nanotechnology. Their existence is a remarkable pinnacle of achievement, an extraordinary coming together of many scientific fields. They combine high-energy physics with traditional technologies such as photo engraving. Look here. Rough spots on these teeth are but millionths of a millimeter high. Our leap into nanotechnology demands unprecedented precision in human ingenuity and human skills.
As humans, we overcome our physical limitations by building machines. Brute muscle power counts for little these days. One finger guiding a power shovel shifts huge amounts of earth. We are extending that same kind of leverage into all sorts of possibilities we discover in the realms of nanospace. From manipulating the very large to the very small with the same human effort. Tokyo University's Department of Engineering developed this microarm. You can use it to shovel earth or control a needle tip within a tolerance of 2 millionths of a millimeter. To give an idea of just how delicate and precise this microarm can be, we compared the tip of its probe to the supposedly sharp point of an ordinary sewing needle. On the left, the tip of the needle. On the right, the tip of the tungsten probe controlled from the microarm. By contrast with the probe, The needle is blunt, its surface marred by all sorts of irregularities. The microarm's tip could write on the point of the needle. There's a saying, the moving finger writes, and having writ, moves on. Devices like this moving finger are writing us ever more deeply into nanospace. Professor Yotaro Hatamura of Tokyo University's Engineering Department.
よく僕自身もまだよくどういう世界ですか分かんないんです。だけど少なくとも今僕らのナノロボットのシステムで1万倍ぐらいを立体視をしながらいじくってみるともう何から何まであっと驚くことばっかりなんですね。それは僕らが知らない世界に自分が1万分の1の大きさになって入り込んじゃったような感じなんですね。相手を拡大するというより自分が小さくなって入り込んじゃったっていう感じがします。
As Hatamura puts it, rather than magnifying nanospace, we have shrunk and gone into it. Here, the microarm's tip is cutting semiconductor wiring 0.003 of a millimeter wide. In this age of microcircuitry, let us hope it is not our fate to shrink to the size of our machines.
Plunge into human engineering of nanospace, we do well to remind ourselves of some of nature's successes. There's Salmonella's propulsion mechanism, for example. The protein motor driving them may be one of nature's most remarkable achievements. Like many microbes, Salmonella is propelled by long, whip-like flagellae. The motor at the base is structurally similar to a man-made electrical rotary motor, with the notable exception that it's built of proteins. As carpenters use different woods for different things, nature creates a specific protein for each and every purpose. Bearing rings, rotor, biochemical motor, and flagellum are made of special proteins. And the whole thing is 300,000ths of a millimeter across. Then there's the tobacco mosaic virus. The tobacco mosaic is one of the simplest viruses of which we have knowledge. Its rod-like form is made up of a single type of protein molecule. The flagellar motor, the tobacco mosaic virus. Two proteins whose structure researchers have worked out. By no means an easy task. To our minds, nature's offerings are both complicated and precise. Look at this. It's a single molecule of a very large protein. This sample of nature's architecture is bacterial rhodopsin, and it is one of the few among countless proteins whose structure we know. It's been studied for its very special property. It reacts to light. Bacterial rhodopsin is composed of some 4,000 atoms, but it works like a single machine, a molecular machine.
So far as we know, bacterial rhodopsin is unique to the cell membrane of a single bacterial species. Halobacterium lives in lakes with high salt content. This purple membrane containing bacterial rhodopsin is a molecular machine that allows the bacterium to capture energy from sunlight. The purple solution contains an extract of bacteriorhodopsin. Scientists have long been able to isolate it, but before they could put this molecular machine to good use, they had to find out how it worked. To meet the world authority on this unique molecule, we traveled to Britain. The British Medical Research Council's Laboratory of Molecular Biology. Dr. Richard Henderson has worked for 20 years to unravel the structure of a single complicated protein molecule, bacteriorhodopsin. Even to the world's most advanced microscopes, the structure of proteins is not actually visible. It has to be elucidated indirectly, step by time-consuming step. First, a cryogenic microscope takes photographs of the protein from many angles. In a three-dimensional object, some atoms will block off others, no matter what the angle. Hence the need for multiple exposures. In practice, this allowed Henderson to shoot right through the stack of atoms to spot the position of each atom in the lattice, some 4,000 in all. Merging the photos gives a 3D picture of the whole. Henderson took more than 10,000 photographs of bacteriorhodopsin over 20 years. His patients rewarded him with a map of a complicated molecule, a three-dimensional protein machine. By January of 1990, Henderson had finally worked out the precise position of every atom in the molecule's lattice.
If we can understand every molecule in biology, let's say in the human, then in terms of structure and function and so on, then we would have a very good picture of how life is working, how the brain is working. And so we're driven to be interested in particular molecules because we think that it will tell us about all of life and all of biology. And after some years of research, you find that even with the simplest little molecule, that once you have investigated it and found out how it works, the mechanism that you end up with, you could not have imagined it in the beginning. So it is like a revelation. It is like reading a new novel that from an author who you have never met before.
This is the result of Henderson's research. Some 4,000 atoms make up a molecule of light-trapping bacteriorhodopsin. The critical component is a small group near the center of the cluster, resembling in shape the Big Dipper constellation. When light strikes, the cluster changes position. This is how the cell traps energy from sunlight. When light hits the molecule, the dipper shifts, raising its energy state. In effect, sunlight winds a molecular spring. When that energy is needed, the spring is released. Despite its complexity, bacteriorhodopsin is 5 millionths of a millimeter across, a tiny molecular machine. Such is the speed of science these days that a Japanese film manufacturer is using bacteriorhodopsin to make an artificial eye. Its instant reaction to light makes it a highly effective optical sensor. Like oil, bacteriorhodopsin floats on water, spreading evenly across the surface to form a thin membrane. Next, the light-sensitive membrane is transferred to an electrode chip supported on a thin glass slide. The chip comes out coated with bacteriorhodopsin, hundreds of trillions of molecules, each one reactive to light. Then a second electrode goes over the first, making the light-sensitive membrane the meat in the sandwich, as it were. As light hits the bacteriorhodopsin, the dipper component changes shape, letting current flow between the two electrodes. This is the result. Light shining directly into the artificial eye shows up in the monitor above it. The optical sensor sees movement, much as a frog's eye does. A frog's eye emphasizes moving objects, screens out motionless ones. One of nature's most profound devices will soon see service in optical discs, computers, and other electronic equipment. Science is learning, and learning fast, how to employ nature's molecular machines. Apart from using nature's proteins, researchers are trying to create new ones, or should we say, proteins which humans have not so far discovered. Human-made proteins, like other experimental molecules, may start as a series of chemical bonds created in special application software on a computer. In this case, the intention is to develop a protein lattice stable enough to serve as the skeleton for a man-made molecular machine. Could humans do the job as well as salmonella? Once a structure is chosen for an experimental molecule, researchers will study the sequence of 4 chemical bases which link to form it. 4 bases combine to make up long-chain proteins such as DNA. Adenine, thymine, guanine, and cytosine, A, T, G, and C for short, can link in any sequence, but the sequence in any one protein is unique to that molecule. These sequences of A, T, G, and C, the 4 bases, literally spell out the blueprint for this particular human-made protein. Next, the bases must be combined in sequence using a DNA synthesizer. Organic chemists jokingly call this a gene machine. The data for a protein consisting of 1,200 ATGC bases took 20 minutes to input and 70 hours to build the sequence correctly. These flasks hold the blueprint for a molecule which, so far as we know, is brand new. Inserted in the bacterium Escherichia coli, the new DNA will reproduce the protein true to type. E. coli is often used to create large batches of man-made organic compounds. It is now possible to design proteins in the same way as new machines, from computer drafting tables to assembly lines. Through 3.5 billion years, continents have split and reformed. The atmosphere we breathe, as well as life itself, is wholly changed. But proteins, life's molecular machines, have used those eons to evolve into myriad forms of organic perfection. Now, human-made proteins are joining their ranks.
of smaller and smaller machines knows no bounds. The latest techniques place the world of the atom itself not so very far beyond our grasp. This geodesic dome-like molecule has been getting a lot of attention among scientists since autumn 1990. It attracts particular interest from people trying to create molecules synthetically. This lattice is made up of 60 carbon atoms, from which the molecule takes its obvious name, C60. Structurally, it's like a 20-sided sphere. Its face is either hexagons or pentagons. In a nutshell, C60 is a tiny, atomic soccer ball. Until recently, we knew two main types of carbon structure. Graphite, used in pencil leads, arranges its atoms in layers of hexagonal lattices. Graphite went into pencils originally because of the ease with which its carbon layers slide off each other and onto paper. Diamond represents the other carbon form. Instead of layers, carbon atoms in diamond are linked in a hard, rigid lattice. Now there is the third carbon type, the one commanding all the excitement in the research community these days, the soccer ball, C60.
To manufacture C60, researchers start out with a thin graphite rod. The graphite is used as an electrode. A high-voltage jolt of electricity is applied across the gap. The voltage breaks down graphite. In its place, carbon atoms reassemble into soccer ball molecules. C60 is very stable. Since the method was perfected in 1990, the C60 carbon type has been made in large batches for experimental use. One limiting factor is cost. $17,000 a gram. C60 mixes with the soot form of carbon in the electrode cavity. It has to be isolated to be of use to scientists. Nevertheless, this black powder is piquing researchers' interest all over the world. One potential for soccer ball carbon is to trap other atoms in its structure, creating superatoms. On the right, a potassium atom shows an electron in orbit around the atomic core. Its outermost electron field determines an atom's chemical properties. With the potassium encased in C60, a single electron begins orbiting the soccer ball, which again behaves like a single atom. Consider what happens if we entrap magnesium instead of potassium. Now, two electrons begin orbiting the soccer ball. Different trapped atoms give modified C60 different properties. It looks as if we are reaching a point where we will be able to write a new periodic table of modified elements. C60 is finding new uses all the time. Take, for example, this alignment of 6 C60 molecules forming up around potassium. It turns out that the tight, rigidly symmetrical lattice is a powerful superconductor of electricity. C60 is a basis for other materials that have no being in nature. Silicon Valley in California, a major home of semiconductor research and development in the United States. Researchers are learning slowly but steadily how to manipulate single atoms as if they were tools. A scanning tunneling microscope. It was originally developed by a major computer manufacturer to visualize single atoms. A report from this laboratory in 1990 caused a sensation. That was the year that researchers, using their scanning tunneling microscope, or STM, succeeded in moving individual atoms.
This represents the surface that we've been looking at today, and on top of this surface we have xenon atoms represented by the blue ball. In order to image the xenon atoms, we take the tip of the STM and we move it along the surface, and it follows the contours of the surface. It goes up and over each xenon atom. What we found is that if we bring the tip close enough to the xenon atom, the force of attraction is great enough such that when you move the tip sideways along the surface, the xenon will follow the tip. We can use this to bring the xenon to some new location.
What Dr. Eigler did in 1990 was to pick up and move individual xenon atoms to spell letters. These were the world's first atomic letters, 35 atoms worth. Eigler is working to refine his technique and extend it, hoping to make single atoms function as microswitches. A microswitch would work like this. Applying a voltage to the tip of the scanning tunneling microscope attracts a xenon atom to it. When the atom is drawn to the tip, an electrical current, the tunneling current, begins to flow. Reducing the voltage causes the atom to fall from the tip, and the tunneling current ceases. Reported in 1991, this is the world's smallest switch, controlling electrical flow much as a transistor does. This technology could miniaturize the most powerful computers. One day, scanning tunneling microscopes might even build atoms into molecular machines.
I hope you enjoyed our ventures into nanospace and human science. I'd like to show you one more thing before we go our separate ways. Here are two among many of science's most recent dreams. A molecular bearing, not unlike those in salmonella, and a molecular car. So far, these are just ideas. But look how far ideas have already carried us. The human desire to delve ever deeper into nanospace is limitless. What kind of nanotechnology will future generations take out of it? We can't even begin to imagine the answer to that question. Still, we have to consider the answer, and carefully. Nanotechnology has already started making slow but steady progress.
The university town of Palo Alto, California. One scientist has contemplated the difficult technical and ethical path into nanorobotics for a long time. The molecular car is one of his suggestions.
A sigma bond bearing
At Stanford University in the United States, Dr. Eric Drexler.
carbon atoms from active
It is Drexler who has made the most far-reaching prophecies for the future of nanotechnology.
A year or two, something like that.
Now we're at long last within sight of what is, in a sense, the end point of that process, the final step, which is learning to get precise control over the arrangement of the fundamental building blocks of matter, down at the molecular, at the atomic scale. With that control, we will at last be limited. The only inherent limit to the technology will be natural law, the fundamental laws of nature. And if those are the only inherent limits to the technology, there will be a greater burden on human law to provide the additional limits that are necessary for us to be able to have the kind of world that we want to live in.
Since our own beginnings long ago, we have surely been asking the questions: what is matter? What is life? We still ask those questions, but now we ask them with a different focus. We are directing our inquiries into worlds within worlds of nanospace. Life for the material world, one thing is certain. We have reached the point of perceiving single atoms. Now that we can see atoms to move them, molecular machines will not be far behind.